Good evening. So let's start with today's lecture. So this is the session 3, and in the earlier two classes we had covered the introduction to the course syllabus. Then we provided the motivation behind the course. So what is the purpose of this? What is the purpose of studying chemical process control? What advantages will it give it to us? Then for this week 0 preliminaries, we covered the Laplace transforms, the basics of it. Then we solved few of the questions related to Laplace transform, and in the next week, that is in the last week, we started with this process modeling and studied about the first order processes and few of these basic terminologies, feed forward, feedback control, all those things. So yes, so in the earlier class we were discussing about these first order processes. So first order system is a dynamical system whose dynamics are given by a first order differential equations. So over here, in general, for any first order system, we can write the differential equation as tau dy by dt plus y is equal to kp x of t. So in process control, it is tau becomes the time constant, kp becomes the process gain, this xt you can call it as your input function or the forcing function, and y are your estimated outputs. So then we studied the response of this first order system corresponding to different type of inputs, step input, ramp input, pulse input, sinusoid input, all those inputs. Then we studied the characteristics of the response inputs, and then we solved few of the questions related to those. So today in week 3 we will be starting with second order dynamical systems. Then we will study its response to the step input, then the effect of the damping coefficient. Then we will solve few of the questions related to this and also cover this FOPTD, that is first order plus time delay process. Then we will cover the basics of this numerical dynamics and as well as the prediction of step response. So this is the agenda for today's class. So today we will be solving around 5 to 6 numericals based on this topic. So yes, a second order system can be given by this equation, that is basically a process whose output can be modeled by a second order differential equation. So over here we are having this equation, which is a second order differential equation. So any process model that can be described by a second order differential equation, we consider it as second order system. And in order to solve such an equation or to analyze the stability criteria given by the second order system, we need to find its transfer function. So in order to find the transfer function, we take the Laplace of this equation and then just write the transfer function in the form of output upon input, that is y bar s upon u bar s, and it will give us this kind of transfer function, that is kp upon tau square s square plus 2 zeta tau s plus 1. So this is the transfer function of a second order system where the parameters are kp, tau and zeta. So kp is known as the process gain of the system, tau is the time constant of the system, and z is the damping coefficient. Now what all examples are available of this second order system? So a second order system can arrive if we are having two first order system in series. Let's say if I am having a surge tank, and if I connect both of this system, let's put agitator. So such a kind of system becomes a second order process. So individually this surge tank is a first order process, whereas this other tank is also first order. So combination of two first order process can become a second order process. Then another example will be a first order process under integral control, So later in the course we will study about this type of controllers, that is proportional controller, integral controller, derivative controller, where we will study that if we apply an integral control to any given system, the order of the system increases by 1. So if we are applying integral control to first order system, let's say for example a level control, then that system will become a second order system. Its order will increase by 1. Then the third kind of examples are the systems that are inherently second order system. So such kind of systems are by default governed by second order differential equations. So one such example of a second order system can be a YouTube manometer that is used to measure the pressure. So this is an example of inherently second order system. Then similarly, second order system can also be represented by this, a block that has been attached to the spring, and if we track the motion of this block, so this is governed by a second order differential equation, so such a system also becomes a second order system. So in general, very rarely this inherently second order system occurs in this chemical process control example. Most of them are the results of these first two processes. So now we have this transfer function of the second order system. Our next aim would always be to find the response of the system given any input. So in the earlier class we studied that in order to find the response of the system, we have to just write y of s is equal to transfer function, that is g of s, into input, that is x of s, and then take the inverse Laplace transform of this function, and that will give us the response in time domain. So in order to find the response of a second order system, for a given step input, we can use this equation where xs will become 1 upon s corresponding to the step input, and then we can take the inverse Laplace and then find the response of the system. So if we take a look on the dynamic response of a second order process in response to a step change in the input. So let's consider a step input of a magnitude a, then it can be represented by this term a upon s. Now in order to find the response, we will just multiply the transfer function by this input, and we will be getting this form. In order to find the Laplace inverse of this form, we need to make this in terms of this partial fraction, and once we have this partial fraction, we can take the inverse Laplace and we can get the response. So once we have this form, we take the inverse Laplace, we write this in terms of partial fraction, and then take the inverse Laplace. So once we take the inverse Laplace, based on this roots of this equation, so these roots of these equations are governed by, you can see the parameters, that is zeta and tau, that is basically damping coefficient and time constants. So the time constant will remain more or less, won't affect the response that much. However, this damping coefficient will contribute to the oscillations in the response. So depending on the value of zeta, we can have multiple kind of responses. So the process response will depend on the value of zeta, and there can be three distinguished cases, that is zeta greater than 1, zeta equal to 1, and zeta less than 1. If zeta is equal to 0, then such a system can be represented by kp upon tau square s square plus 1. So this is an example of an undamped system. That is for zeta equal to 0. When I say undamped system, it means that the output will oscillate with the same amplitude, whereas in case of a damped system, the output will either keep on decreasing to a constant value, or it can just the amplitude can keep on increasing exponentially. So on the basis of this different values of zeta, we can write the solution via these equations. So for zeta is greater than 1, we call such a system as overdamped system, and the response is given by this equation. For zeta equal to 1, we call the system as critically damped system, and for zeta is less than 1, we call the system as underdamped system. And for underdamped system, we have this equation. So you don't need to remember each of this equation, you just need to understand the solution methodology, so how to basically find this response given any inputs. Now, few of the characteristics I have just mentioned over here, that is, responses exhibit a higher degree of oscillations and overshoot as zeta approaches to 0. That is, if zeta is very close to 0, then the oscillations will be higher and also the overshoot will be higher. So we will study what overshoot is. Then larger values of zeta will yield a sluggish response, that is basically there will be a delay, so the steady state value will be reached slowly if the value of zeta is higher. So let's consider if zeta is 2 for this case, over here the value of zeta will be 1. Then the fastest response without overshoot is obtained for a critically damped case, that is for zeta equal to 1, the response will be the fastest for such a critically damped case. Now I have just written all those things again over here. So we can estimate whether the given system is an overdamped system, critically damped system, underdamped system on the basis of these values of zeta. And similarly, as we studied, the transfer function was written as gs kp upon tau square s square plus 2 zeta tau s plus 1. Now if the system is overdamped, that is zeta is greater than 1, then we can also say that the roots of this equation, that is the roots of the denominator, will be real and unequal. So basically, if I am having a plane where this is my real axis and this is my imaginary axis, then the roots of this equation for zeta greater than 1 will be real, that is, it will lie on this half of the plane. And by unequal, I mean to say they won't be the same, the magnitude can change. No, so since they are only real, they will be lying on this axis. Similarly, for critically damped system, that is zeta equal to 1, the roots of this equation will lie on again x-axis and they will be the same. That is, they will be either plus 1 or minus 1 or plus 2 or minus 2, whereas in case of this overdamped system, they will only lie on this axis. And in case of zeta less than 1, that is underdamped system, they will form a complex conjugate. That is, they won't be on x-axis, they will be either on in this 4 quadrant, but not on the axis. So if we see the response plot corresponding to the step input of a second order system, then corresponding to this zeta equal to 1, that is critically damped system, we will see the response given by the blue line, that is the steady state, that is the response will be the fastest for the critically damped system. Now for overdamped system, that is zeta is greater than 1, the response, you can see it is sluggish and it will reach the steady state later. So similarly for underdamped, and both of these systems, that is critically damped system and overdamped system, won't undergo oscillations, whereas in case of underdamped system, we can see that the response is oscillatory and eventually it will reach the steady state, that is this value. Now we are looking at the plots for this overdamped, critically damped system, overdamped system and underdamped system based on different values of zeta. So for critically damped system, that is zeta equal to 1, we already discussed that the response will be such a plot. Whereas if we keep on increasing the values of zeta, that is if we keep on increasing the damping coefficient, the response you can see will become more and more sluggish. Now in case of underdamped system, for a step input underdamped system, for the response of the step input to the second order system, we can see if we keep on decreasing the value of zeta, the oscillations will keep on increasing. So for zeta equal to 0.2, the oscillations are higher, and for zeta equal to 0.4, the oscillations are lesser. So these are the 2 points that we discussed by this points also. That is, for if zeta approaches 0, the degree of oscillation will increase. That is observed from this plot. Similarly, for large value of zeta, yield a sluggish response. That is, if we keep on increasing the value of zeta, the response will become more and more sluggish. Now we will study few of these performance characteristics of the step response of an underdamped process. That is, we will basically analyze the plot and define few of these terminologies which will help us understand the characteristics of this second order curve. So this is the plot corresponding to a underdamped system. So the first thing to note is rise time. That is the time taken by the process to reach the new steady state value. That is, if I am starting from this point 0 and my steady state value is 1, then the first instant, that is time taken by the system to reach the first instant of the steady state, that is basically this time, we call it as rise time. So the system may not be stable at this point. Eventually it will undergo oscillations and then reach a steady state point, but still rise time, we define it as the first instant at which the steady state has been reached. Now the second time is the time to first peak. So this is self-explanatory, the time required by the output to reach its first maximum value. So over here the maximum value, or you can say the amplitude, will be maximum at this point, and the time taken to reach this point is time to the first peak, that is tau p. Then the other time is the settling time, that is the time required for the process output to reach and remain inside the band whose width is equal to plus or minus 5% the change in y. So basically at this point, after this point, we can say that the response will be lying within this bounded range of 0.95 to 1.05 times of the steady state value. And the time taken to reach this state is known as settling time, that is tau s. Apart from this, we can also define this time period, that is time taken to reach to successful amplitudes. So basically time taken by the system to cover this much amount of amplitude. Similarly, we can also say that the time period can also be defined as in this time period between two crests of the response. So this will again remain same for each of these different oscillations. Over here also the time period will remain same and it will be p. So we covered the settling time period. Now then the other two parameters are the overshoot ratio. So the overshoot, we denote it by A by B. That is the response that the overshoot above the steady state. So this is our steady state value, and the magnitude of the response above the steady state value, that is A, to the magnitude of the response below the steady state value, that is from our initial state. So this is B. So this ratio A upon B, we call it as overshoot. Similarly, we define this decay ratio. So decay ratio is defined as the ratio between two successive peaks. So over here in the decreasing order. So basically over here, if the height is C, and if this height is A, then the overshoot, then the decay ratio, we define it as C upon A. So decay ratio is C by A, whereas this overshoot we call it as A upon B. Now this decay ratio will remain same for consecutive oscillations. So over here for this segment, if I find the decay ratio, it will become D by C. So if I call this as D, so the decay ratio will become D by C, and this will be equal to C upon A. Similarly, the overshoot ratio will also be the same. Can you mute yourself? Okay. So now we will study first we studied the characteristics of the second order process, and we defined few of these parameters, and now we will find the mathematical formula for each of those terms. So the first term we studied was the time to the first peak, that is the time taken to reach the first maximum value, that is given by tau pi upon under root of 1 minus zeta square. Now second, we defined this overshoot ratio, so it is given by this formula exponential of minus pi zeta upon under root of 1 minus zeta square. Then we defined the decay ratio, that is the ratio between two successive peaks, that is also the square of overshoot, so it is given by this formula. Then finally we define this time period, that is 2 pi tau upon under root of 1 minus zeta square. So these are these three main formula you need to remember, that will be helpful in solving most of the questions related to the second order system analysis. Then over here we are having the relationship between different performance characteristic, that is overshoot ratio, decay ratio, time period, with respect to the damping coefficient, that is zeta. So if we keep on increasing the zeta, the time period of the system will decrease, that is time between two successive peaks or the bottoms will keep on decreasing as we increase the damping coefficient. Similarly, if we keep on increasing the damping coefficient, the overshoot ratio as well as the decay ratio will keep on decreasing. That is, as the system moves to zeta equal to 1, that is to critically damped system, the overshoot will keep on decreasing. Now, so this until now we studied about the response of a second order system, and we studied few of these characteristics of it. So now we will study this first order system plus time delay, that is also we call it as FOPTD in short form. Later we'll study about the basics of stability analysis related to the pole and zeros, so that is basically the numerator dynamics, and then we will solve few of the numericals later in this class. Now, why do we need to perform this FOPTD? So in chemical engineering systems, you can say that majority of the systems are governed by you can say they can be a combination of the multiple first order systems, that is 1 upon tau 1s plus 1 upon tau 2s. Similarly, for higher order systems, we can see that the response will become sluggish. So in order to approximate such higher order systems, we can approximate them by using first order plus a time delay factor. So let's say if this is my response of a first order system, then for a second order system we can get such a response also. So here we can see that there is a time delay. You can approximate this as constant, and then this part you can again consider it as a first order system. So ultimately this entire curve corresponds to a second order system, but we can also approximate it as a first order plus time delay system. So this much amount of part we call it as time delay or tau d, delay time, and then later on we can approximate this by a new first order system, not the same as the original one. So there are different techniques in order to approximate any given system into FOPDD system, that is first order plus time delay system. So two commonly used techniques or discussed in the course are, the first one is Taylor series based approximation, and the second is this half rule, commonly called as Skogastad's half rule. So we'll call it as the half rule formula simply. So let's consider a given process that is given by this transfer function 1 upon s plus 1, 1 upon 2s plus 1, and let's say 1 upon 3s plus 1. Now for any FOPTD process I can represent it as, this is an approximation, so I can write this time delay term as minus of tau ds upon tau bar s plus 1. So my aim over here is to transform this higher order system into FOPTD system. So for that I need to find the new parameters of the system, that is this time constant of the process and the delay time. So there are these two rules for Taylor series based approximations, that is one rule to find the time constant, that is this value, and another rule to find the time delay of the system. Similarly for this half rule formula, the time rule or the time constant is found by these heuristics, and similarly the time delay is found by this rule. So basically by Taylor series approximation we can get that the process time constant will be a dominant time scale of the transfer function. So due to the presence of this, so over here if we take a look at different time constant of the process, so for this s upon 1 time constant is 1, that is coefficient of this s term. Over here time constant is 2, and over here the time constant is 3. So this time constant 1 and 2 are less as compared to this 3, so the response for this system will be faster, but the response due to this higher order, the response due to this high time constant will be sluggish. So we call this as the dominant system. So if we use this Taylor series based approximation for this FOPTD, we can write the process time constant is simply tau, that is for the new system tau will be 3. Then if in order to find the time delay, that is tau d, we can write the sum of all time constants excluding the first dominant time constant. So over here time constant, the first dominant time constant is 3, so we will just exclude this and sum the remaining 2. So we will remove this term and the sum of the other two terms, that is the other two time constant will be 2 plus 1, it will be 3. So the new system, that is basically FOPTD approximation, will become e raised to minus of 3s upon 3s plus 1. Similarly, now we will study this half rule formula. So as the name suggests, half rule, what we do is we keep the dominant time scale of the transfer function and then we take half of the next dominant time scale. So over here time constant will become, this was our dominant time scale, that is 3, plus half of the second dominant, that is 2 by 1, that will become 1. So over here time constant will become 4, and then the sum of So this is basically tau, and now we need to find the time delay. So time delay will be the contribution of the second dominant time constant will be half plus all remaining constant, and we have to again remove the first time dominant time constant. So over here it will become 2 by 1 plus 1, that is basically 2. So the system in this case will become, FOPTD system will become e raised to minus of 2s upon 4s plus 1. So this is our FOPTD based on this half rule formula. So such a kind of systems mostly occur due to the series combination of first order systems, and they are typically overdamped. So since they are occurring as this multiple first order system, we won't be seeing the oscillations, and they will be usually of the form of this overdamped system. That is why we approximate them as first order plus time delay FOPTD. FOPDT, yes. And then, so such kind of model can also be obtained from actual data or higher order transfer function. So let's say if I am having a stirred tank heater, so this is my response, this is my input X. So at this instant I provide a step input to the system, and if I found the response experimentally, I can get such a plot, and based on this plot I can get my FOPT. So this I will approximate it as tau d, and over here I can just fit my first order transfer function, that is Kp upon tau s plus 1, and get the desired parameters in order to find this FOPTD model from data. Now, why do we need to study this? Now the next topic is this numerator dynamics. So when I say numerator dynamics, it simply means that I need to calculate the poles and the zeros of the transfer function, and on the basis of the poles or zeros of the transfer function, I can predict whether the system will be oscillatory or non-oscillatory, or whether it will be stable or not based on this. So that is why we study this numerator dynamics. Basically, on the basis of this, we can predict the nature of the response of any given dynamical system. So how do you define poles and zeros? So basically, if we write the transfer function in terms of numerator upon denominator, then the roots of the numerator are called as the zeros of the system, whereas the roots of the denominator are called as the poles of the system. And then we have few of these stability criteria, that is a dynamic system is stable if it is having the poles on the left hand side of the imaginary axis on a complex plane. So we discussed it earlier also. So if this is my real axis and this is my imaginary axis, so if the roots of the denominator lie on this half of the plane, then we can say that the system is a stable system. Whereas even if it has one pole, so if there are multiple poles of the system P1, P2, P3, and if any of this one pole lies on this half of the system, that is right half of the system, then the system will become unstable. And over here the system is stable. So that is why we can analyze the stability of the system by calculating the poles and zeros of the system. Now we can study few of the response of the second order system in MATLAB, and then we can move on to solving the questions. So meanwhile, if you have any doubt in the theory discussed until now, you can ask, or if you have doubt in earlier classes, questions related to earlier classes, then you can ask and I can try to solve them. Later, after that, we will try to solve the numericals related to the topic discussed in today's class, that is second order system plus second order system, then first order plus time delay systems, and few of the questions related to these poles. So I will just show you demonstration to how to calculate the response of these systems in MATLAB. So first step is to define our variable, that is S. Now we can write our second order transfer function. Let's just call it as system1 S. So let's just find the response of this overdamped system, that is 4 upon overdamped system. I'm writing it as 4 upon S square plus 5 into S plus 4. So this is the transfer function corresponding to overdamped system, and if it is subjected to a step input, I can straight away use the MATLAB's inbuilt function in order to find the response corresponding to the step input. It's SYS1. Then we can just run it. So this is the response of a step input for the given second order system. So over here the denominator is given by S square plus 5S plus 1, and on the basis of the zeta that can be inferred from this denominator, we can say whether the system is overdamped and underdamped. So in this case the zeta will be greater than 1, that is why this is an overdamped system. Now let's take a look for the effect. If I keep on increasing the value of zeta, that is basically if I keep on changing the coefficient of this middle term, what are the effect on the response? So we studied that if I keep on increasing the damping coefficients, the response will become more sluggish. So we will just check whether we are getting the same response in this plot or not. So I will just define a new system in which let's just call it as 25. So I'm increasing the value. Let's just call it as 6. So either it will become underdamped system or overdamped. Let's just see what response we'll be getting on the basis of this. So if we take a look at this orange graph, it is corresponding to sys1, that is when the middle term was 5. Whereas the second plot, that is slightly yellowish, corresponds to sys2, where I have increased the value of the middle term. That is basically I'm increasing the damping coefficient. So you can see that the response will become more sluggish in this case. Similarly, let's take a look on this underdamped system. Let's just close this plot. So an example of underdamped system is this 4 upon S square plus S plus 4. 4 upon s square plus s plus 4. Now let's just compare the response of both of this overdamped system as well as underdamped system. So as we studied, the underdamped system will be oscillatory. So let's just check whether we are getting that or not. So yes, this orange graph over here corresponds to this SIS2, that is our underdamped system. So over here we can see that the oscillations have increased in case oscillations are present in case of this underdamped system, whereas in case of overdamped system it is simply straightforward. Now we can study this critically damped system also. So critically damped system is given by the middle term as 4. I'll just run that. So over here we can see the response corresponding to each of these plots. That is, the oscillatory one corresponds to this underdamped system, this green line corresponds to critically damped system, and the yellowish orange line, this third line, corresponds to this overdamped system, that is zeta equal to 1. For oscillator it is zeta less than 1, and for this green line it is zeta equal to 1, critically damped system. Now we already also discussed about this one case of undamped system where this zeta becomes 0. So let's just plot that also. So this term is 0. So due to this presence of the undamped system, we can see these high oscillations in the system. So over here you can see that this is basically due to the response of this undamped system. That is, the oscillations will be of constant magnitude. If I just zoom into this, you can see that there are these oscillations of magnitude 2 at top as well as bottom, and these oscillations won't damp, that is, the amplitude won't decrease for the case of undamped system, whereas for the case of this underdamped system the oscillations will eventually decrease and it will reach the steady state. That is what I wanted to convey by this exercise. Now since we are in MATLAB, let's just try to demonstrate this FOPTD also. First order So let's take an example of this system that we discussed. That is, if the transfer function is given by this term 1 upon, let's say, s plus 1 and 2s plus 1, and for this system I have to write a FOPTD model that is basically G in terms of e raised to minus of tau d s plus tau s plus 1. So we can use both of these rules, Taylor series as well as the half rule, to find the process time constant tau and time delay. And we will just compare the plots of this original transfer function, then both of FOPTD models from both of these approaches. So Taylor series approximation says that the most dominant time constant will be the time constant of the process. So over here time constant will become 2, whereas the time delay will be, we have to neglect the most dominant time constant and then sum all the remaining. So over here there are no more further time. Once we neglect this tau equal to 2, we are only left with this tau equal to 1, so that will be our time constant 1. So this model I can write it as e raised to minus of s upon 2s plus 1. Similarly, based on this half rule formula, for it this time constant was defined as the most dominant plus half of the next second best dominant. That is basically 2 plus 1 by 2 will become 2.5. Similarly, time constant was defined as we have to neglect this first term and then take the half of the second dominant and then sum of the other three. So over here it will simply become 1 by 2, that is 0.5. So this FOPTD model will become e raised to minus of 0.5s upon 2s plus 1. Now we will compare the response of each of this model corresponding to a step input. So let's just define our original system. So this is our higher order system. One divided by s plus 1 into 2 s plus 1. Then based on this Taylor series, it was e raised to minus s upon 2s plus 1. Based on this half rule, it was exponential of minus of 0.5 into s divided by s. So over here it is 2.5 plus s. So this is our original model, that is a combination of two first order process. This we want to approximate in FOPTD, that is first order plus time delay. So this is the approximation using Taylor's approximation, and this is the approximation using the half rule. Now we will find the response corresponding to this step input. I'll just simply write step input of this hold on step input of So now we are plotting the response of each of these three processes. Just do it again. So this is the response corresponding to the step input, and over here we can see that this orange line, let's just start with this blue line. So blue one is our original system. Now we had to approximate this blue line by using first order plus time delay. So the first approach was this Taylor series approximation, and this orange line shows the approximation from this Taylor series. So over here we can see that it has added a time delay of around 1 second. It has added a time delay, and after that it has approximated it as a first order system. That is basically it is approximating it as first order plus time delay. So ultimately the steady state value of the given system will be more or less similar to the original system, but the transient at the initial stages might be a bit offset, so it will be a bit more inaccurate. Then this orange line, this yellow line is the response from the half rule formula. Over here the time delay will be less, and ultimately it will reach this same step response of the original system. That is, both of these approaches are doing a reasonably good job in approximating this higher order system by using this FOPTD. So similarly, given any higher order system, we can approximate it by first order plus time delay systems. So now we are done with theory, and we will start with solving the questions related to this. So this is the first question that you have to solve today. So the question is decay ratio for a system having a complex conjugate pole just dash is this. So over here, for a given second order system with step input, we have been provided the complex conjugate poles, that is basically the roots of the denominator of a second order transfer function, and we have been asked to find the decay ratio for this given systems. So I will give you a couple of minutes to solve this question. So right now it is around 8:01. So I will give you around 5 minutes to solve this question, and you can try solving this question. So given the complex conjugate poles, you have to find the decay ratio for this system. And we studied the decay ratio of the system as this formula. So you can note down this formula, that is exponential of minus 2 pi zeta upon under root of 1 minus zeta whole square. So we have to find the decay ratio for given this information. If you have any doubt related to solving this question or any of the topic discussed today or earlier in the class, you can unmute yourself and ask, or write it in chat box also. Yes, so I think yes, that answer is correct. 9 into 10 raised to minus 3. So do you want to go through the solution? I think we can move on to the next question then. So is the correct answer is 9 into 10 raised to minus 3. So basically what we do is, I will just discuss the solution methodology so that the others who will watch this video will get the solution methodology. So the second order transfer function, we write it as 1 upon tau square s plus 2 zeta tau s plus 1. Now over here we have been given that the poles of the systems are this, that is basically minus 1 upon 10 plus or minus of, so these are the poles of the system. So we discussed that poles are the roots of the denominator. So we can find the roots of the denominator, and it will be, I think, minus zeta upon tau plus or minus of under root of zeta square minus 1 upon some term. I'm not sure about this. So basically this we have to compare it with this term, and then we will be getting the equation in terms of minus zeta upon tau is equal to minus 1 upon 10 and some term is equal to 2 by 15. And so on the basis of solving this equation, we will be getting the value of damping coefficient zeta, and then we will be using the formula of the decay ratio to find this. So if we look at the poles of this system, this I think will be this term. So basically the poles of the second order systems are given in that questions were this term, that is zeta upon tau plus or minus of under root of zeta square minus 1 upon tau. But since the poles were complex conjugate, we have to provide a j over here, so this pole will become zeta upon tau plus or minus j upon under root of zeta square minus 1 upon tau, and later we can compare these coefficients with the solution that has been provided. So that will give us the final answer, that is the decay ratio for this system as 9 into 10 raised to minus 3. Now we will go through the methodology behind this second question and then try to solve it. So the second question is, a unit gain second order under damped process has a time period of oscillation, 1 second and a decay ratio of 0.25. The transfer function process is dash. So over here we have been given the period of oscillations, that is tau is equal to 1 second and decay ratio as 0.25. And then we have to find the transfer function of the given system, that is we have to find this parameter tau and damping coefficient zeta. So using these two information, we have to find the value of tau and zeta and then replace it over here, and we will get the desired answer. So the formula for the time period of oscillations was 2 pi tau. It is given by this equation, 2 pi tau upon under root of 1 minus zeta square, and then the decay ratio is given by this equation, exponential of minus of 2 pi zeta upon under root of 1 minus zeta square. So we have to use these two formula in order to find the value of zeta and tau, and then replace it in the equations for the second order system, and then we can get the transfer function of this process. So I think this is a very straightforward question, so you can try solving this on your own. We will move on to the next question in a couple of minutes, so once you are done solving this. So I will share the solution at around 8:15. So I'll just share the solution with you and you can try solving it on your own later. So yes, as I discussed, so you have to find this constant tau and zeta using these two information. So for time period, we have the formula. Similarly, we have the formula for decay ratio. And on the basis of that, you can get the value of zeta as 0.2154 and the value of tau is 0.1554. And you can replace it in this equation in order to find the transfer function. That is, option A was the correct one, and this is obtained by using the value of tau as 0.1554 and the value of zeta as 0.2154. Now this is a fairly simple question. This is question number 3, where it is given that a step change of magnitude 2 is introduced in a system having the following transfer function. The percentage overshoot is dash. So over here the step change we have been provided, that is the input is 2 by s, and we have to find the percentage overshoot. So for overshoot, we have the formula as exponential of minus of pi zeta 1 under root of 1 minus zeta whole square. So given this information, you have to find the percentage overshoot that is present in the system. So you can try solving this. I will discuss it in 2 minutes, the solution in 2 minutes. Yes, so that is the correct answer, 16.3. So if we try to verify this solution, we can try verifying this solution in MATLAB also. So let's just find the response of the second order system. But first let's discuss the solution methodology behind this. So yes, as I discussed, we have been given this transfer function, and using this we have to find the value of time constant and damping coefficients. So the first thing is to transform this equation in this form, that is tau square s square plus 2 zeta tau s plus 1. So this thing we need to keep in mind, the last term should be 1. So we will divide the denominator by 4 and then transform it in the desired form. And then the coefficients of the denominator we will compare, and on the basis of that we will be getting the value of tau as 1/2 and zeta also has 1/2, and then we will be using the value of damping coefficients zeta in this overshoot formula, and then we will find it around 16.3%. So overshoot, as we studied, it was let's just plot it in such a manner. So if this is C, if this is B, this is A, then the overshoot ratio we define it as B by A. So let's just try to find the response of this function, s square upon 2s plus 4. So this is our transfer function, and I have to find the step response. So this is the response of the given second order transfer function for a step input of magnitude 1. So let's just, so the overshoot ratio won't depend on since it is a ratio, it won't depend on the absolute magnitude. So we can calculate the overshoot percentage from here. So just an approximate idea that the steady state of the system is around 0.5, and the maximum value is at around this point. So it is around, so the amplitude is around 0.58. So this part above the steady state value will be 0.58 minus of 0.5. So we will just calculate the decay ratio approximately by using the plot. So it will be 0.58 minus of 0.5. Sorry, 0.58 minus of 0.5 divide by, so this part above the dotted line is 0.08 and below it is 0.5. So this comes around approximately 0.6, and in percentage it will become 16%. So that is from the plot also we can see that the decay ratio is around 16 to 16.3%. So that is the significance of calculating the decay ratio from the formula, as well as the significance of basically the characteristics of the second order system that we studied, that is decay ratio, overshoot ratio, all those things. Now we will look on to the next question. So this is a fairly lengthy question. So I will give you around let's say 8 minutes, around 8:30 we can discuss the solution. So the question is, for a unit step input, the response of a second order system is given by these equations, where Kp is the steady state gain, zeta is the damping coefficient, tau is the natural period of oscillations, phi is the phase lag, and we have been given the formula of the overshoot. Then for the unit step input, the response of the system from the initial steady state condition at t equal to 0 is shown in the figure below. So the response corresponding to these equations we have been shown in the plot, and we have to find the natural period of oscillations of the system. So basically we have to find the time period of oscillations in this case using the given plot and whatever the formula we are having. So basically, given this plot, we have to find the time period of oscillations for the given system. So again, you can try solving this. I will share the I will discuss the solution later. So this plot will be useful to you. That is why I am keeping the plot in this slide. So in this question, just to repeat, we have been asked to find the natural period of oscillations, not the time period of oscillation. So I think you have already solved all of these questions. So these are basically questions from the past year GATE. So yes, I think the answer is no, answer is not 63.2, it is 15.9. 63.2 is the incorrect answer. You can try solving this, and then I will just discuss the solution. Okay, I will explain the solution. So given this plot, we have to find the natural period of oscillations, that is tau. So I'll just copy this plot. So we have to use this plot and we have to find the value of tau. So tau is basically this term. So if I calculate the time period of oscillation, it will become 2 pi tau upon under root of 1 minus zeta square. So this term is natural period of oscillations, or whatever thing that we have been asked in the question. So in order to find this time period of oscillations, the first thing we need to find is we need to find the value of zeta. But in the question we have been only provided this plot. So using this plot we can find the we need to find the value of this zeta, that is basically damping coefficient. But from the plot we don't have any direct information about the damping coefficient. We only have information about this time period of oscillations, then overshoot ratio, decay ratio, steady state value, all of these things only we are having. So if we analyze this plot, we can see that the system reaches the steady state at this point. So if I take a look onto this first oscillations, so this length will be 350 minus of 250, that is equal to 100. So this part, let's just call it as A, is 100. Similarly, we can find the distance between the maximum response and the steady state value or the ultimate value. So the ultimate, this part we can call it as B. So the value of B will become 430 minus of 350. 430 minus 350 is 80. So once we have this B upon A, we can calculate the overshoot. So overshoot we defined it as B by A. So in this case, in this scenario, it will become this B we calculated as 80 and A we calculated it as 100. So overshoot ratio will become B by A, that is 80 upon 100 is equal to 0.8. So now we are having the value of this overshoot ratio. Similarly, from the plot we can find the time period of oscillations, that is the time taken to reach two successive peaks or two successive bottoms. So over here, let's just delete this stuff. So over here, this is our one peak, this is the second peak. So this time is time period of oscillations, that is T. So we can see that this time period of oscillations is this part and this part. So this is 0 and this is 200. And since we are having 4 segments between them, so each segment is of 50. So this will be 50, 100, 150, 200. So this entire duration, that is time period, is 100. That is time period we found out as 100. So from the plot we are having this basic information, that is time period is 100 seconds and the overshoot ratio we calculated it as 0.8. And now we will use the formulas of both of this term that we were having and try to find the value of zeta. So the first thing was overshoot ratio was exponential of minus of pi zeta upon under root of 1 minus zeta whole square. And this term we found out as 0.8 from the plot. So in order to solve this, to find the value of zeta, we can take the log of this term. That is, this term will become minus of pi zeta 1 under root of 1 minus zeta whole square upon ln of 0.8. So ln of 0.8 will be minus of 0.22314. And on the right hand side, since we are having minus, let's just cancel it out, and then we will be having zeta upon under root of 1 minus zeta whole square is equal to 0.22314 upon 3.14. So this will become and ultimately we will be calculating the square of this term also, so it will become zeta square upon under root of 1 minus zeta square is equal to 0.22314 upon 3.14 whole square. Am I correct? Yes. Now let's try solving this. 0.22314 divided by 3.14 and square of this whole thing. Sorry again. So this is approximately equal to 5 into 10 raised to minus 3. That is 5 point, let's just call it as 5.05 into 10 raised to minus 3. So you can take the inverse of this thing, 1 minus zeta square upon zeta square, and this will be approximately equal to, let's say 1 by 5 is around 2 into 10 raised to minus 3.2 into 1000. So this will be approximately equal to, let's say 200. So we can further simplify it as 1 upon zeta square minus 1 is equal to 200. Then zeta 1 upon zeta square will become 201. Then zeta will become 1 upon under root of 201. That is 201 under root 14. That is 1 by 14. 1 upon 14. So approximately it comes around 0.0714, the value of damping coefficient. Let's just call it as 0.07. So now we have found this damping coefficient, and the other information from the plot that we had calculated was a time period of oscillations was 100 seconds. Now we'll be using these two information in order to find the natural frequency of oscillation, that is tau. So the formula for time period of oscillations was 2 pi tau upon under root of 1 minus zeta square, so is equal to 100. So you can just put the value of zeta over here and find the value of tau as 100 into under root of 1 minus of 0.07 whole square upon 2 pi. Yes. So this will become 0.07 square. It is 1 minus of 0.0049. So this is approximately equal to 100 upon 2 pi. Let's call it as 100 divided by 6.28. So this comes around 16.02. That is approximately equal to 16. If you solve accurately, you can get the formula. So yes, the formula, the answer that we calculated from this was 16 minutes. And And yes, the initial period of oscillations is also 15, around approximately equal to 16 minutes, that is 15.9. I hope the solution is clear to you. If you have any doubt, I can again go through the solution. Yes, this recording will be available after the meeting also. So the recording, if you see, if you go into this NPTEL, so this is the NPTEL course page from where you will be accessing the course. So over here, we have this section of problem solving sessions of August 2023. Then in this, we are having problem solving session recording. So over here, you can just click this link and it will take you through this Excel sheet. Over here, you can see the previous recording. So this was the recording of our last lecture. Similarly, you can find the course content in this link also. So over here, for my session, I have just uploaded the content of week 1 and week 2, where you can see the slides of these questions. The full slides that I am presenting are available. Also, you can just find the notes related to the discussion. So this is available on our NPTEL course webpage. For other sessions also that is conducted by my colleague, you can again see the course content in this section. So I hope the solution of this question number 4 is clear to you. If not, I can just discuss it again, or else we can try. So I think right now we are having 20 minutes remaining. So we can try solving questions related to other topics. So this is the question related to the first order plus time delay systems. But again, we can try to solve this. So over here, we are having a term on the numerator also. But still, the methodology to calculate the FOPTD approximation will remain same from both the approaches. So you can try solving this and then we can compare the solution in MATLAB of both of this question. So over here we have been given a transfer function and we have to approximate the first order plus time delay, that is FOPTD model for this given system. So if you just want to go through both of these rules, I'll just repeat it again. So in the Taylor series approximation, the process time constant is the dominant time scale, that is the largest time constant, and the time delay will become the sum of all the time constant, but we have to remove the largest time constant. Similarly, everything remains same in the half rule method, just that we have to add the half of the second dominant time constant in both of this process time constant also, as well as the time delay also. This is not the question. This is the question that we are looking on. Tau equal to 5 and tau d equal to 3.5. Let me just check the solution over here. So we are having this term will also correspond to some delay in the system, delay, or since it is in the numerator, so yes, it will cause a delay in the system. So you need to account for this thing also. So the time delay will become, what you had suggested was 3.5, but it will become 3.5 plus 0.1, that is 3.6. Then the time constant is same, 5. So this is from Taylor series expansion. Now you can use the same approach to solve, to approximate using half rule formula. So similarly, we can try solving this for Skogegastad's half rule. So for that, we study that time constant will be the most dominant time constant plus half of the second dominant time constant. So over here again the most dominant time constant is 5, the second dominant is 5. So it will become 5 plus 3 by 2, that is 6.5. Similarly, the delay time will become, we have to neglect this first term and take the half of the second dominant term, that is basically half of this, that is 3 by 2, and then sum all the remaining time constant, that is plus 0.5 plus 0.1, that will become 1.5 plus 0.5 is 2, 2 plus 0.1 is 2.1. That is the time, the FOPTD from this half rule formula will become k e raised to minus of 2.1 s upon 6.5 s. So these are both the approximation, and we'll compare the response with the response plot using MATLAB also. I will paste this code in the notes so that if you have access to MATLAB or this toolbox, you can try solving this. So again, FOPTD Now the transfer function, let's just call it as original transfer function is given by, let me pull it over here. So the original transfer function, let's just take the value of k as constant as 1, the numerator was minus of 0.1 into s plus 1 upon 5 into s plus 1 So we can check the plot of this function. So this is our original function that we want to approximate using FOPTD. So just from the plot you can see that initially the value is close to 0 and then ultimately it starts to rise. So this term we can approximate by this time delay term and then fit the first order process. That is what these approximations do. I'll just write the other transfer functions. So from the Taylor series, we obtain the transfer function as exponential of minus of 3.6s upon 5 into s plus 1. So this was the transfer function we obtained over here, 3.6 and 5. Similarly, from half rule we got the transfer function as the time constant was 2.1 and it was the time delay was 2.1, time constant was 6.5. So now we can check the response in this plot. So this red line was our original one. Now this second plot is basically from the half rule, and the third plot, that is the yellowish plot, is from the Taylor's formula. So yes, basically ultimately by this we can see that all of these approximations are able to approximate the higher order system into first order plus time delay system. Now we will try solving the last question. So this question also will again solve using the MATLAB. So this question is, for the given transfer function, we have to plot the poles and zeros in a complex plane using MATLAB, and then from the pole locations in the complex plane, what can be controlled about the output modes for any input change. And also then we have to plot the response of the output to the step input, and thus the form of your response agree with your analysis in part B that we have to discuss. So you can try, you won't be able to solve this manually since we are having a fifth order polynomial in the denominator. So I will just show you the solution in using MATLAB. So the numerator, let's just call it as numerator is this term. So we write that the poles are the roots of the denominator, whereas zeros are the roots of the numerator. That is, zeros are roots of numerator, whereas poles are the roots of denominator. So let's just find the both of these things. So in order to find this roots, we have to provide the coefficients of the polynomial. So that will become 1, 2, 2. Similarly, the coefficients of the polynomial, that is of the fifth order polynomial, for this denominator will be 1, 5, 2, 4, corresponding to s we are having 0, and then it is 6. So yes, the zeros we have obtained it as, I'll just write it over here. So these are the zeros and these are the poles of the system. So over here we can see that the zeros are complex as well as the poles are also complex conjugate. But over here if we look at this pole, over here the imaginary part is 0. That is basically we are having the real part that will lie on x-axis. And we studied that for the system to be stable, all the poles should lie on the left half of the plane. But since the presence of this pole 4.7681, the system will be unstable. That is, the output won't be bounded. So we can, another thing to plot or find the pole, basically plot the poles of the system in this complex conjugate plane. We can use this formula pz plot of the transfer function. So transfer function we are having is this one. This term. So this is the plot that we are getting. I'm not sure if it is visible online. So over here we can see that these x are corresponding to the poles of the system, whereas the circles are corresponding to the zeros. So it is mentioned. So this 0 is -1 plus 1i. Similarly, this is -1 minus 1i, and the rest are the poles. So over here we can see that there are these poles that are lying in this right half of the plane. That is why the system will be unstable. So we can check that by plotting the response of this, the step response of this transfer function, so that we can simply do it using step of response. So yes, this is the response of the given system. So initially it was 0, then after let's say around 110 seconds, the oscillations will start and the value will keep on increasing. So the output is not bounded. That is why we can say that the system is unstable. So this happens because of the presence of this pole on this right half of the plane. Yes, that is what we conclude from this last question. So yes, I will provide all of these codes and questions in these notes and you can try solving them on your own. So in today's class, basically what we discussed was the second order responses corresponding to the step input and the FOPDD process. And then we studied about this numerator dynamics related to poles and zeros. So we tried solving those and analyzing those systems in MATLAB also. Yes, I think that's all for today's class. We can end today's meeting.